So Module 3 is reactive chemistry, and reactive chemistry is very cool. I like reactive chemistry. It's it's just cool. It's one of my favorite topics that I did in chemistry, just because it feels very like chemistry. It feels like what the movies say chemistry is, if you know what I mean. But if you don't, that's fine. So an important thing to remember when we talk about reactive chemistry is the difference between physical and chemical change. So here's just a comparison. So physical change is the form of the matter is altered, but the substance itself is not transformed into another. So for example, like changing states, so water going from liquid water to ice to water vapor, that's a physical change because it's not changing this actual substance into something that isn't water. It's just changing its form. So these are usually reversible, like changing states is reversible, and the intermolecular forces change. Then we have the chemical change process. So process in which substances are altered involving the rearrangement of the atoms. So this is, for example, going from an acid and a base to salt and water. The acid and base it doesn't just change state to become a gaseous acid and a gaseous base. It changes into something completely different chemically. So it's a rearrangement of atoms. Some signs of chemical change, is that like a color change, odor, release of gas, those kinds of things are usually signs of chemical change. And in the terms of like writing a reaction, chemical change, a new substance is formed. Something that you didn't have before has been completely made. So that's that. When you talk about changes in physical or chemical changes, it's important to talk about the changes in force. So keep that in mind when you're talking about physical and chemical change and when you're thinking of reactions. So the first part of the syllabus is talking about different reaction types, I guess. And so the first reaction type that we have is a synthesis reaction. So it's called combination in the image on the right, but it's known as synthesis in the syllabus. So this is when we have one substance A, let's say, and then we have substance B, and they combine together to make one substance that is made up of like A and B. So if you look at the example, we have the Haber process, which is something you'll learn in year 12, and we start with nitrogen and hydrogen gas, and then what happens, it makes ammonia, and it still has that nitrogen and the hydrogen in it, but now it's rearranged into only one product, so two become one basically. The opposite end of the spectrum is decomposition reactions, where we have one product breaking down into one reactant breaking down into two products. Not one product, one reactant breaking down into two products. So in synthesis, we have two reactants becoming one product. In decomposition, we have one reactant becoming two products. So if you look at the image, it does a good job of kind of showing you what's happening with like the little smiley face circles. But an example is this reaction where carbonic acid is changed into water and carbon dioxide. You can tell what's kind of happening in the reaction by the names. So synthesis, you're making something. Decomposition, you're breaking something apart. So that can help you remember how many products and how many reactants there are. So that's the first type of reaction. It's very simple and it's very easy to identify. The next type of reaction we have is combustion. So combustion I always associate with fire, and burning. And basically this helps me remember that it's exothermic. We'll talk more about what exothermic and what endothermic means a little bit later in module 4. but exothermic basically means that it produces heat. So it's an exothermic reaction that involves the burning of fuel in oxygen. So the word equation that we use for it is fuel plus oxygen is carbon dioxide and water. So that's complete combustion. Complete combustion means that there's excess oxygen, there's enough for the fuel to completely combust. But sometimes in an environment where there is not enough oxygen, we have incomplete combustion occur. So this can form fuel, this is the reaction between fuel and oxygen again, but instead of forming carbon dioxide and water, it forms carbon monoxide, so CO, and soot, which is just carbon as a solid, and water. So sometimes incomplete combustion is just fuel plus oxygen is carbon monoxide and water. Sometimes it's fuel plus oxygen becomes soot and water. Sometimes it's fuel and oxygen becomes carbon monoxide, soot, and water. So it's different. It's different depending on the how much oxygen there is. So if you have very, very limited oxygen, you'd get just soot and water. If you have a little bit more oxygen, then you'll get carbon monoxide and water. And then if you have excess oxygen, you'll have carbon dioxide. So a good way to remember this is complete combustion is when there's excess oxygen. So that one in the products, it has the most oxygen molecules. So carbon dioxide has 2 oxygens, whereas carbon monoxide only has 1 oxygen. So that's incomplete versus complete. So that's just how I remembered my incomplete and complete combustion. There's lots of different ways to remember it, but that's just how I did it. So that's one reaction, and this is a very important reaction to remember because this comes up again in Year 12 and also in Module 4. So it's important to know this one. So the next one is another very important one because this comes up again in Year 12, and this is a precipitation reaction. So this is when the reaction between 2 aqueous solutions produce an insoluble solid, and this is called the precipitate. So if you look at the little image, the precipitate is that blue stuff at the bottom, and the equation, when you have the states in the equation, it should be 2 aqueous makes an aqueous and a solid. And a common question when it comes to precipitation is identifying what product will be the precipitate, which will be the solid. And to do that, you use your solubility rules. So solubility rules are very important, especially in Year 12, but in Year 11, at least for my school, we were given solubility rules when we needed them, but we weren't expected to remember it until we got into Year 12. So I'm not sure if that's what happens at every school, but I thought it's safest to just assume that we need to know solubility rules. It's always good to just know them because it will make it quicker. But yeah, so the best way to remember solubility rules, at least the best way for me to remember solubility rules, is the acronym NAGSAG. So these are all groups that are soluble. So the N is for nitrates, the A is for ammonia, G is for group 1, sulfates, acetates, and group 7. And then the little asterisks, if you look at the bottom, there are a couple of exceptions. So if sulfate is with calcium, strontium, or barium, it becomes insoluble. And if group 7 ions are with lead, magnesium, or silver, it also becomes insoluble. So yeah, it's something that you'll have to remember. Yeah, know your exceptions. So for sulfates, how my teacher explained it to us was the exceptions for sulfates are Castro-Bear, so Ca for calcium, Str for strontium, and Bear for barium. And then for group 7, the exceptions were PMS, so P for lead, PB, and for magnesium, Mg, and S is for silver, which is Ag. So the Moving on, basically the the only way to do precipitation is with your solubility rule. So that's something worth getting to know and getting familiar with. If you can get familiar with it now, it will take less time for you to memorize them when you get into year 12. So just a thought. And acid reactions. So again, acid-base reactions and acid reactions are very important in year 12. You do a whole topic on acid bases and their reactions. So it's very worth paying attention here. So basically you have three main acid reactions that you're expected to know in Module 3, and the first one is acid-base, also known as neutralization. So what happens is you have an acid, you can usually tell it's an acid because there is an H at the front, and then you have a base, and you can usually tell it's a base because there is an OH at the end. And these combine to form a salt and water. If you look at the example, hydrochloric acid and sodium hydroxide form sodium chloride and water. And then that's acid, base, and salt and water. So yeah, pretty self-explanatory there. The next reaction is acid carbonate reaction. Again, another important one because this also comes back in year 12. But for this, what happens is you have an acid and you have a carbonate, so it's a metal carbonate usually, and this forms a salt, and it forms carbon dioxide and it forms water. So the example is a reaction between hydrochloric acid and magnesium carbonate, and yeah, it's just balanced out there. But an important thing to note is when you perform this type of reaction, since carbon dioxide is being formed, what you'll notice is there will be bubbles coming out of the solution. So whenever you see bubbles, that means that there's a gas being produced, and it's just a matter of being able to tell what gas is being produced. So you'll notice in the acid-metal reaction, you have an acid and a metal causes salt and hydrogen gas to be formed. So there's an example with hydrochloric acid and magnesium. So if you had these reactions and you were asked to determine whether it was an acid carbonate or an acid metal, just based on the fact that there were bubbles produced, something that you can do is collect the gas and test which gas was produced. So there are different tests to figure out what gas is being produced. For hydrogen gas, it's the pop test, so stick a flame in and there should be a popping sound, and for carbon dioxide you've got the lime water test, so it turns milky if there's carbon dioxide. So that's a way to differentiate them if you ever need to. So those are the acid reactions, and so yeah, this is a practice question that I think is very good. So the question is, which of the following correctly identifies the gas or gases produced when hydrochloric acid is reacted with zinc, sodium hydroxide, sodium carbonate, and sodium hydrogen carbonate, respectively? So, if we go from the first reaction, which is hydrochloric acid with zinc, that's an acid-metal reaction, so we know that it forms hydrogen gas. So that leaves B or D as our answer. So we'll keep narrowing it down between those two. The next reaction is a base. So sodium hydroxide has that hydroxide, which usually indicates a base, and it's with an acid, so that forms a salt and water. Now, neither of those are gases, so no gas is produced, so B and D are both still in the running. So sodium carbonate, we have a sodium carbonate, so a metal carbonate and an acid reacting. So when that happens, we know that that forms a salt, carbon dioxide, and water. Now, carbon dioxide is produced, so again, B and D are both still in the running, meaning that we just have to really figure out what the reaction between an acid and sodium hydrogen carbonate is. So, in this situation, you have an acid, which is hydrochloric acid, and sodium hydrogen carbonate. It is a really good idea to write down what the equation is. So what you'll find is it's hydrogen chloride, so HCl, plus NaHCO3, which is sodium hydrogen carbonate. And what that makes is NaCl, so sodium chloride. And then what you have left over, so that's your salt. And then what elements or pieces that you have left over is you have that H from the hydrochloric acid, and then you have the HCO3 from the hydrogen carbonate, part of sodium hydrogen carbonate. So what it will form is water and carbon dioxide. So you're not forming any hydrogen gas in this reaction, so therefore you're just forming carbon dioxide. So D will be your correct answer here. So yeah, that should be your process in this kind of question, just narrowing it down, going through all the reactions, and then figuring out which option is right. So D is the correct answer in this case. Yeah, so moving on. That was the first inquiry question all done, which was very quick. Yeah, basically for the first inquiry question, it's really just knowing those reactions. Like that's really all you really have to do for it, and all you really have to know. So know those reactions, and you're all set for the first inquiry question. Then we have the second inquiry question, which is, I think, the toughest one in Module 3. So we'll go through this one in quite a bit of detail, but this is all about predicting the reactions of metals. So we'll talk about the reactions of metals in water, dilute acid, which we've kind of already talked about, and oxygen and other metal ions in solution. We'll talk about some patterns in metal activity on the periodic table, which correlate with ionization energy, atomic radius, and electronegativity, which are all concepts that you should have covered in one of the earlier modules. And then we'll look at redox. So redox is quite difficult. It may take some time to understand, so we'll take some time on that one. But yeah, we'll just get started right into the second inquiry question. So first, looking at the reactivity of metals with water, well, yeah, basically metals that are more reactive will have a faster rate of reaction, so you'll see a more aggressive reaction typically with more reactive metals. For example, sodium in water, it reacts quite violently and quite aggressively, so you have to look away quickly or else it will burn your eyes. On the other hand, if you put lead in water, nothing happens. So that's just an important thing to note, that reaction rate is very different depending on what metal you're putting in the water. And in general, what happens is water plus metals creates hydroxide salts. So for example, if we're putting magnesium in water, we'll create magnesium hydroxide and also hydrogen gas. So some things to note about water reacting with metals is that some react with liquid water, some react with steam, others don't react with liquid water but do react with steam. So some react with both. It's all it depends on the metal. So that's that. And also another thing is that a decrease in the temperature of the water increases reactivity of some metals, including potassium, sodium, lithium, barium, calcium, and there are also some metals that don't react in water at all, so they do not form a hydroxide salt and a hydrogen gas, and this includes lead and copper and gold. So just some things to think about. If we look at yeah, we'll look at that next anyway. I don't know why I was getting ahead of myself. Yep, so moving on, we have metals with acids. So we know that when acids react with metals, it produces salt and hydrogen gas. We talked about that before. Some differences between more reactive metals and less reactive metals is that more reactive metals would produce lots more bubbles, which indicate the hydrogen gas, than the metals that are only a little bit reactive. Those will have less bubbles and smaller bubbles. So potassium and sodium react quite vigorously, so lots of bubbles, and the hydrogen gas can easily ignite. So like I talked about before, there's the pop test that can determine that it's hydrogen gas, and that's because hydrogen gas is flammable. So yeah, lots of hydrogen gas can ignite. Then magnesium and calcium react with dilute acid with less bubbling. Zinc, aluminium, tin, and iron have very slow bubbling, and then some have no reaction at all. So that's that really. I don't know really how to explain this without just saying you kind of have to just remember these reactions. So you have to remember that a water and metal is a hydroxide, a metal hydroxide. Oh, sorry, a metal hydroxide and hydrogen gas. And then you just have to know that in this case it's a salt and hydrogen gas being produced. So yeah, just keep this in mind. Know that if it's more reactive, lots of bubbles, less reactive, smaller bubbles. And when we look at the trends in the periodic table and how it can help us determine metal reactivity, it'll be much easier to figure out whether something has slow bubbling or whether it's bubbling a lot. So that's something to look forward to later on in this lecture. But yeah, so when we talk about reactivity of metals with oxygen, metals and oxygen form a metal oxide. Who would have guessed? But basically how this metals and oxygen can be determined by experiments where it's heated in the presence of air or plunged into a glass container with oxygen. So some trends in the periodic table, that magnesium, aluminium, zinc, and iron, they burn readily and form oxides. A thing to consider is that iron oxide is rust. So that's just something interesting, I guess. So iron oxide can be the rust that you find, and that means that without oxygen, rust can't be formed. So if you put rust, like an iron nail, in a vacuum sealed container, theoretically you can't have rust being formed. But that's not the point of this. So yeah, lithium, sodium, potassium, calcium, and barium, they also burn readily and they form peroxides. So an example is sodium peroxide there. And then you have some that react slowly to form oxide layers known as rust. I just talked about rust just then. Iron oxide is also a type of rust. Yeah, you're not really burning anything to form a rust, so it occurs much slower. And yeah, it's just like the outer layer. Then we have silver, platinum, and gold, which has no reaction at all. And an interesting thing that my teacher pointed out to us when we were learning this is, if you think about silver, platinum, and gold, they're all metals that are used very often in jewelry. And if we look back at the other side, you'll also see that gold, platinum, and silver have no reaction with acid, and it also has no reaction with water. So you have gold over there and platinum. So it's important to think about why those were chosen for making jewelry, and it's because that jewelry is always in contact with oxygen, and if you're washing your hands with like rings on or a bracelet on, you might get water on it. You don't want it to be violently reacting, or else that would be really bad. So the reason they chose those metals for jewelry is because they don't react. They don't react to acid, oxygen, water. They can just be. So that's something to keep in mind, something interesting, and just a little nugget of general knowledge. So yeah. So another thing is the reaction of metals with other metal ions. So it can be determined by observing if the metal in the solution displaces the solid metal, so a metal displacement reaction. the more reactive metal goes into solution generally. So an example is if we put copper solution with magnesium solid, what will happen is you'll see a deposit being made around the magnesium strip that was originally in there, and that's copper solid, and then the magnesium is going into solution. It's becoming aqueous. So we'll talk more about metal displacement reactions when we talk about redox. But first, what we'll talk about is trends in the periodic table. So just to recall and recap, the trends in the periodic table from the previous modules, we have atomic radii, the radius of the atom. Pretty self-explanatory what that is, but the trend is that it increases down a group. So if you look at the little diagram at the bottom there, you'll see that the radius gets bigger down a group, and then across a group, the radius gets smaller, so it decreases across a period. Not a group, sorry, a period. And then first, ionization energy. So just recall that ionization energy is how much energy is needed to remove the first valence electron in a gaseous state. So that increases across a period and it decreases down a group. And the same trend is shown in electronegativity. So just again, another recall is that electronegativity is how likely it is to attract an electron to form a bond. So this also increases across a period and decreases across a group. How this ties together with the reactivity of metals is that as ionization energy increases, reactivity of metals decrease. As atomic radii increases, the reactivity of metals increase. As electronegativity increases, reactivity of metals decrease. So putting it in more in better context, if we looked back here, we'll see that ionization energy increases across a period and down a group. So as ionization increases, so it's increasing, so ionization energy increases across a period. So ionization energy increases across a period. That means that across a period, the reactivity of metals decreases. So the more to the right you go, the less reactive the metals become. And yeah, so if you just follow the trends of ionization energy, atomic radii, and electronegativity, you'll be able to figure out the patterns in the periodic table of where the most reactive metals are. So in general, if we look at the periodic table down here, I know it's quite small, but the more reactive metals are up here in this corner here, and it becomes less reactive the more you spread out diagonally this way. So that's a general rule of thumb. That's something you can keep in mind when thinking about what bubbles more, what bubbles less, all of that stuff, what has a more vigorous reaction, what has a slow reaction, what has no reaction. So we see that gold and silver are on the far right side of the metals, and same with lead, which we also saw before was not very reactive in water. So if you remember some of those key ones that don't react and the key ones that do react, so we remember that sodium is very reactive in water, and that lead is not very reactive in water. We can kind of guess the kind of spectrum and where it's more reactive, where it's less reactive, if you know what I mean. So yeah. So that's that. Here's a kind of a summary of the reactivity of metals. So we have the most reactive up there going to the least reactive down at the bottom. I won't read out the whole list, but another thing is if you look at the reduction potentials on your data sheet, it follows a similar list. So if you look at that, we'll talk about that data sheet when we talk about redox, but yeah, if you're ever stuck in an exam and you don't know your reactivity series of metals, if you look at that data sheet and you look at their potentials, it's going from most reactive to least reactive, top to bottom, generally. So yeah. So we're going to look at redox reactions now, which is a little bit tricky, so we'll spend some time doing them. But basically, redox reactions are a type of reaction that involves the transfer of electrons. So there are two parts of a redox reaction, oxidation and reduction. And the way we remember what each one is oil rig. So oil is oxidation, is loss of electrons, and then rig is reduction, is gain of electrons. So basically, when you have a redox reaction, one compound is getting oxidized and the other compound is getting reduced. And some terminology that you have to be familiar with is the oxidizing agent, or the oxidant is the species that causes the other one to be oxidized. So it does not itself get oxidized, it's reduced. So it's quite confusing, but the oxidant or oxidizing agent is reduced, but it causes the other to be oxidized. So it's just best to remember that it's opposite. So an oxidizing agent or oxidant is reduced. And then a reducing agent is oxidized. So it's a little bit confusing, but like all things in chemistry, it starts out confusing, but the more you practice it, the better you get at it and the less confusing it becomes. So for redox reactions, the first thing to remember is oil rig, oxidation is loss, and reduction is gain. And the way that we are able to determine whether a loss or a gain is happening is when we look at oxidation states, which we'll talk about in a bit. So if we look at this net ionic reaction here, we can see if it's redox or not. So let's look at it. So we have, this is an example of the metal displacement reaction we talked about a couple slides back, but we start off with aqueous copper, and then we have magnesium solid, and then this reacts to form magnesium aqueous. Ooh. Sorry if that sounded weird. My earphone just like fell out. Anyway, so we have magnesium aqueous then, and copper solid. So is this redox? Let's see. So we have copper as an aqueous. We'll look at one at a time. So when we're looking at a reaction and determining if it's redox or not, the best way to do it is look at one species. So we're looking at copper and then determining what happens to its electrons there. And then we look at the other one and see if the opposite is happening to its electrons. So if copper was gaining electrons, that means the magnesium has to be losing electrons. That kind of thing, we have to figure that out. So the questions we ask ourselves are, is there a transfer of electrons happening? And then we can figure out which is oxidized and which is being reduced. So if we look at copper, copper starts by being like an ion that is 2+. So it's 2+, that's fine. It's a little bit positive. Then what happens is when we come on to the other end of the reaction, copper has gone to being just a solid, being not an ion, not charged, it's neutral. So we've gone from positive to neutral. How does that happen? That means we needed a negative to counteract that positive. So that means that copper was gaining electrons to become that solid copper. So the aqueous copper was gaining electrons to counteract that positive charge to become the neutral solid copper. So that means it's a gain, which means it's part of the rig, oil rig. It's reduced, so copper is reduced. If we look at magnesium, we start with a neutral solid, so it starts just as magnesium, and then it becomes an ion, it becomes positively charged. How does that happen? We needed to add a positive, and how you add positives is basically you're taking away negatives. So basically it's losing electrons, and without those electrons it can't balance out the positive, which makes it positively charged here. So that means that magnesium is losing electrons, which means it's part of oil. Oxidation is loss, so it's oxidized, so magnesium is oxidized. So all of that I just said can be summed up into these half equations here. So if you just look at those, you'll see that copper plus 2 electrons, so that's a gain, that's reduction, it becomes copper solid. Then magnesium is oxidized, so it loses 2 electrons. So together it's a redox reaction. Something a little bit more complex that goes down in the redox kind of syllabus is that it can occur in an acidic solution, and this requires a few more steps than just adding electrons to either side of those half equations. So how you go about these is you have 4 main steps. First, you balance all the elements aside from hydrogen and oxygen, so you ignore those to begin with. And then what you need to do is to balance that oxygen, you add water, so H2O, you add water to the other side of that oxygen. And then to balance the hydrogens that you added from the water, you just add hydrogen ions to the other side, and then you balance the charges. So what this looks like is if we're looking at acidified permanganate to solid manganese oxide. Sorry, my words got a little jumbled there, but if we're going to acidified permanganate to solid manganese dioxide, we first write out this equation. So it goes from the acidified permanganate to the manganese dioxide. Then we need to balance the atoms that aren't hydrogen and aren't oxygen. So this is basically already done. And then what you need to do is you need to add water to help balance oxygen. So as you can see in that little equation there, we've added water, and this is just 1 oxygen to begin with, but then since we put a 2 in front of the H2O, that means it's 2, so it becomes the 4 on the other side. It's just all balancing equations. That's another thing about redox. It's very important that you're confident in balancing equations, because there's quite a lot of balancing of equations here. But yeah, you just follow the steps that I mentioned before. So we added the water to help balance the oxygen, and now that we have the oxygen all balanced, now we just have to balance the hydrogen. So the 2 H2s means it's 4 hydrogens that we need to add to the other side, and then we need to balance the charges by adding electrons. So you have 2 neutrals on the other side, and we need to make sure that it's 2. It's also a neutral on the left side. So on the right side, since you have the solid and the liquid, those both don't have any charges. Charges is 0. But on the right side, we have that 1 negative from the acidified permanganate, and then we have the 4 positives from that hydrogen ion. So that means that overall we need 3 electrons to balance it out, and there you go. So it's a lot of just balancing equations, really. But just remember those 4 steps. First, balance other atoms other than hydrogen and oxygen. Add your water to balance oxygen. Add hydrogen ions to balance the hydrogen, and then add your E's to balance the charge. All of that balancing can get you that final redox equation. Sorry, just fixing my little earbud there. So as I talked about before, the standard potentials on your data sheet in chemistry, it can help you understand the reactivity series of metals. So it kind of follows the same pattern, but also it shows us the strongest oxidant and weakest oxidant, strongest reductant and weakest reductant. So basically, going from top to bottom, it becomes a stronger oxidant. So it becomes more likely to lose electrons. And then from top to bottom, it becomes a weaker reductant. So it is more, it's less likely to gain electrons the further down you go. And how this ties in with your reactivity series of metals is that your more reactive metals are therefore more likely to want to reduce. They're more likely to yeah, they're more likely to reduce and less likely to oxidize. So, yeah, that's basically that. We'll talk about using these standard potentials in a practice question in a second, but just remember the oxidant is the oxidizing agent, and this is more likely to let me start that over again. Oxidizing agent causes the others to oxidize. It does not itself oxidize, it is itself reduced. So keep that in mind when looking at this. Okay? Cool. So, oxidation states is another thing that's in the syllabus, and it's a little bit weird, but basically oxidation state represents the number of electrons that an atom can gain, lose, or share when chemically bonding. And if there's an increase in an oxidation number, that means that an oxidation reaction has occurred, because that increase in oxidation number means a decrease in electrons, which means you're losing electrons, which means oxidation. Then a decrease in oxidation number means a reduction reaction occurs, because that decrease in oxidation number means that it has become more negative, which means that more electrons have been added on, which means it's gained electrons. According to Oilbrick, gain means reduction, therefore a reduction reaction has occurred. So here are some of the rules about oxidation states. So the first one is that the oxidation state of elements on their own is 0. For example, zinc as a solid, sodium as a solid, it's all 0. And it's the same for elements in molecule form. So for example, oxygen and hydrogen, that's O2 and H2. Their oxidation states will also be 0. And the oxidation state of an atom as an ion is the same as the charge of an ion. So the oxidation state of zinc ion is 2, and the oxidation state of a chloride ion would be -1. So yeah, that's pretty self-explanatory. I just think of oxidation states as like the exact same as the charges, basically. That's the easiest way to remember it. If it's ever different, they'll let you know. But another thing is that the sum of oxidation states in a neutral compound is always 0. So yeah, just simple maths can help you work that out. And then also the oxidation state of oxygen is generally 2 negative. So yeah, it's 2 negative. 2 minus. That's something that you might need to use in a redox reaction, but there's not much I can say about it other than that's what it is. And yeah, oxidation state of hydrogen is usually +1, and oxidation of fluorine is usually -1. So those are the general rules for oxidation states. You'll just need to remember them. The more that you look at redox questions, the more that you'll remember these rules, really. So we'll just move on. Yeah. Oh, okay. There we go. So, if we look at this question, so oxidation states, let's look at this practice question. Which is the oxidizing agent and which is the reducing agent in the following reaction? So, if we look at this, if you remember from the rules, H2 has an oxidation state of 0. So, that's 0. And, yeah, O2. We know O2, 2, 0. Yeah, so I'll just, okay, I'll just explain this with my words then. So we start with a 0, and then basically what happens in H2O, that H is, the H is a +1 oxidation state, there's 2, so it's +2. So the H goes from the H side, it goes from 0 to +2. That means it's lost electrons. That means it's been oxidized. If it loses electrons, it's oxidized, which means that hydrogen is the reducing agent. Because if you remember from my little spiel earlier on, the oxidizing agent is not oxidized, it's reduced. So the reducing agent is not reduced, it's oxidized. So if H is going from neutral to +2 in oxidation state, that means, what does that mean? That means that it's going neutral to +2, which is more positive, which is a loss of electrons, which means it's oxidation. So if H is being oxidized, if hydrogen is being oxidized, that means it's the reducing agent. Okay? Then we have oxygen. So if we look at oxygen, in that form, it's 0. The oxidation state is 0 because that's how it is as a molecule. And it becomes -2 in that gaseous water there. So it goes from 0 to -2. It's more negative. The oxidation number has decreased between the reactants and the products, which means that electrons have been gained. So since electrons have been gained, according to oil rig, it's been reduced. So reduction is gain. So oxygen has been reduced, which means that oxygen is the oxidizing agent, because oxidizing agents get reduced. So you see how it is a little bit confusing? Like, even I'm tripping over my words here because I'm saying like reducing and oxidizing so much, and it's so easy to get confused. So it's very, very important that you solidly understand what oxidizing is, which is loss, what reducing is, which is gain, and then what oxidizing agents and reducing agents are, which is completely separate to oxidation and reduction. It's the opposite way around. So it's a lot. I know it's a lot, but it's something that has to be done. But yeah, that's basically how you go about working out your oxidizing and reducing agents based on your oxidation states. So yeah, we can move on. So a common thing that comes up in the syllabus and in questions regarding redox is the galvanic cell. So these are devices which utilize chemical energy released by redox reactions to generate electrical energy. And here are the key parts of a galvanic cell. We have the electrode, where the metals are placed within solution. We have the anode, where it's the negative electrode, and the cathode, which is a positive electrode. So how you remember that anode is negative and the cathode is positive is it's the same as anion and cation. So cations are positive ions, so the cathode is a positive electrode, and then the anions are negative ions, so anode is the negative electrode. The anode is where oxidation occurs, and again, I find some fun ways to remember what happens where, because it can be quite confusing. So how I remember it is oxidation is loss, and loss is negative. You don't want to lose something, that's bad. So it's at the negative electrode, and then the cathode is positive, reduction gains it, gains electrons, it gains something, something is added, that's a plus. So reduction occurs at the cathode. Another key thing that's a part of the galvanic cell is the salt bridge. So the salt bridge is filter paper soaked in a salt solution. Most of the time it's potassium nitrate. That's because potassium nitrate just does a really good job of what the salt bridge is supposed to do, which is something we'll talk about in a second. But yeah, so those are the key parts. Then we also have the electrolyte, which is a substance in aqueous or molten state that conducts the electricity. So yeah, that's that. And all this is set up with that voltmeter, and the electrons flow from anode to cathode. How I remember it goes that direction is we go from A to C. A is before C, so we go from anode to cathode and goes through the voltmeter, and that generates electrical energy, that movement of electrons. So we'll go into more detail about this. As I said before, electrons always flow from anode to cathode, and basically at the anode, oxidation is occurring. So as oxidation occurs, it's losing electrons, and those electrons are then free to move through the voltmeter and into the other side of the galvanic cell, where it can be gained by whatever is being reduced. So yeah, that's what it looks like. If we look at the example here, we have zinc and copper. So if we look at our little reaction situation, our reduction potentials, we'll see that copper is more reactive than zinc. Since copper is more reactive than zinc, what's going to happen is that that copper is going to be reduced, and when it's being reduced, it's gaining electrons, and it will form a deposit over the electrode. And then in the zinc side, it's just in solution, and it's moving those electrons across. So yeah, the salt bridge is very important. It basically is just a house of ions. So you have, it's usually potassium nitrate, so it's just potassium and nitrate ions. And these ions are able to move and can therefore stabilize the charge in each of the half cells. So the half cells is obviously like the zinc half versus the copper half. But the cations in the bridge move towards the cathode and the anions move towards the anode, and this prevents the cathode from accumulating negative charge. So the cations are positive and they move towards the cathode to prevent it from becoming too negative. And then the anions, which are negative, they move towards the anode and prevent it from becoming positively charged. So that's the salt bridge. It plays a very important role. You can't do the galvanic cell without the salt bridge. So that's something important to remember. So now we'll talk about cell potentials in these galvanic cells. So how you go about these kinds of questions are firstly to determine the half equations, and then use the table of standard reduction potentials that is on your data formula sheet. You look at there, look and find those half equations that you determined were a part of the galvanic cell. And then what you do is you calculate the total cell potential by adding those together. It's important to note that on the data sheet, they're reduction potentials, not oxidation potentials. So what you'll be needing to do is for the oxidation half reaction, you'll need to change that that potential into the opposite sign, basically. So we'll go through an example so you can see what I mean. But yeah, we'll do that. So a practice question is, a strip of magnesium metal is placed in an aqueous 1 molar solution of copper sulfate solution. Will a spontaneous redox reaction occur? So what we need to do is we need to find out what that potential of the redox reaction is, and we do that with the half equations. So first thing that you need to do is find out the half equations. So wrote those out here. Magnesium becomes magnesium aqueous and 2 electrons, and then reduction, copper plus 2 electrons becomes copper solid. Then what you do is you look on your data sheet, and what you'll see is that we have magnesium, which is the normal one. We use the opposite of, sorry, let me rephrase that. Sorry, that was really badly worded. Okay, so on the data sheet, basically the copper is being, is the reduction. Copper is being reduced. So you're using that normal potential. Then magnesium, it was originally a negative, but since we're flipping the equation around, it's become a positive. So then what you need to do is just add it together, and then what happens is you have 2.7. Since it's positive, that means that it is going to be spontaneous. So I should have led with that, but if the potential of the redox reaction is positive, that means it is going to occur spontaneously. So at the end, you should always write a concluding statement, especially since the question was like a worded question. Like in maths, if it's a worded question, it's best to give a worded statement at the end, not just numbers. Same thing with chemistry, you should always have a little concluding statement to make it very clear that you think that it will be positive at the end. You think that it'll be spontaneous because it's positive. So add that in where you can.